Welcome, everybody, for another episode of our podcast. I'm delighted to have with me today Mr. John Fite. John, welcome. Thank you so much for joining us.
Hey, thanks a lot for having me. Glad to be here.
Great, great. John is a 2007 graduate of Adfontes Academy. He has his BS in physics from Grove City College, a master's in physics from Albany. And while at Albany, he actually studied nanoscale technology, nanoscale engineering.
Nanoscale engineering, yep.
And now works at the applied physics, works with applied physics through Johns Hopkins University, and is in fact a Ph.D. candidate at the illustrious and esteemed Johns Hopkins University. John, what an impressive credentials you have. I feel like we could just end the podcast right here and now. It's like, oh, yeah, look at that. One of our grads is a PhD candidate at Johns Hopkins. And, that's it. Okay. But it's very impressive. It's great to see you again. Tell me, John, a little bit about how you came to be interested in physics and science, some about your educational story.
Mm-hmm. Sure, absolutely. Well, definitely. Thanks again for having me on. It's great to be here. I guess I'll go a little bit further back and kind of tell. So when I was much younger, maybe like 10, 11, 12 years old, part of the, drive, I naturally enjoyed science, math, just like the way it seemed, just like that mode of thinking. And so enjoyed those subjects in school. So figured I'd probably move in that direction. I think some of the path for physics and nanotechnology got set pretty early. Kind of a funny story about that. When I was 10, 11, 12, I really liked laser guns, but thought through, if I really wanted to build a laser gun, I actually need a really powerful but miniaturized power source in order to have kind of like a nanonuclear battery or something like that to provide power for my laser gun. So in order to do that, maybe I should do physics, and Grove City going for physics there. Figured that's a good stepping stone for nanotechnology. And then from there, went to nanotechnology after that.
Did you ever build your laser gun?
Not yet. No, I think still a couple technical hurdles to jump through to get there.
When I was a kid, when I was I would daydream about having like a rocket launcher and blowing up all of the cars on my block. They're like, is this, did you think similarly? Like if I have a laser gun, I can shoot my brother like right between the eyes or something. Like, did you envision like destruction and chaos and you reigning above it all?
There may have been a little of that. I feel like there's, maybe a little bit. So,
good. So from a 10, 11-year-old, you have this idea about building a laser gun, and that's cool. So as you advance and find out more of the math and so forth, and to pursue, you've got to really love this if you're pursuing it at such a high level. Physics, applied science, what is it? Why do you think, what connects with you about this field? Why do you find it so enjoyable and enchanting, we might even say?
Sure. I'd say, I definitely enjoyed calculus and physics at Adfontes. I think that was kind of like a first taste, and I appreciated the fact that physics was coming from not only a immediate dump of modern technological knowledge, but more tracking all the way back from like Zeno's paradox and tracking from some of those original thinkers. And it was kind of interesting just to see that trail of thought up to the present day.
Zeno's paradox. Tell us about that.
So I'm a little rusty, but my understanding of it is basically he was arguing there is no such thing as motion, because if you were to, as a thought experiment, take a picture of an arrow moving through the air and then take another picture a microsecond later or less, it would look like it's exactly the same, and you wouldn't be able to tell that there's been a change from one to the next. And so he was arguing for this, and I think I don't remember who he was arguing with, but one of his opponents stood up and walked across the room and said, no, obviously we can move. So,
Right. So, some of those classic debates of the pre-Socratics, right? Whereas even that, so it's interesting, even early on, you saw this connection between philosophy these kind of like thought experiments of philosophy and the hard sciences.
Mm-hmm. And I think actually, it's funny you mentioned that, because I think that that's one of the beauties of that interaction is the joining. One thing I like about science, and maybe I'll get into this a little bit more, is the fact that it does join the thought experiments and the kind of intuition, creativity, just thinking about the world, with tying it down to objective reality and experiments in the world. So coming up with testable hypotheses, the basics of the scientific method. Thinking, coming up with a testable hypothesis, and then having to pin it to the real world and say, yep, it actually holds up, or no, it doesn't.
Yeah. Mm-hmm. Interesting. I think I don't know really anything about physics, and motion is not something I know much of. But time, of course, I know physics has to think about time a lot, and time too is a slippery sort of concept. It seems like the moment you try and measure it, it's gone, right? It's not there. So what exactly are you measuring? Since once the moment is gone, it is gone. I'm sure physics has to wrestle with a lot of philosophical problems like that, I imagine.
Absolutely. In fact, that's actually one of the in terms of my Grove City experience. So did AFA, went to Grove City, and pretty much knew I wanted to do physics from the beginning. And I think one of the professor at the time, who was head of the department for the incoming students, the way he described physics is really you're learning systematic problem solving. So engineering, for example, I think is a very valuable skill. Oftentimes it's based on solving particular styles of problems and getting very good at solving those problems. Physics, you learn a couple very generic fundamental equations like F equals ma, or some of Maxwell's equations. And they're sometimes very concise equations, but have very broad applicability. And so part of what you're learning in physics is systematic problem solving, where you can look at even a problem that you haven't quite seen before. You may have seen similar things before, but you have been given a toolbox of some very general equation tools that you can then use to unpack that equation, or unpack that problem, break it down, and systematically solve for each component. And so that's I like that aspect of physics, systematic problem solving. I also enjoyed, while at Grove City, my later couple of years, I did some research in the lab and started to appreciate not only the coursework side of science, but the research side, and really found that I like research. There's a hands-on component to working in the lab and doing experiments and building samples that you can look at under a microscope that's very satisfying and has a different rhythm and feel than homeworks or tests, for example.
Right.
And that was actually a big selling point for going to grad school was, wow, I really like research. It's just very different from the conventional rhythm of homework and tests. And so I think that was definitely a key experience there. We were working at that time, it was called nanotechnology research. Really, we were doing MEMS, which is micro electromechanical structures. So it's not quite nanoscale, but we were building these different micron scale structures. The other thing I liked about physics was moving from base level physics of learning, how does the ball fly through the air, to things like quantum mechanics and relativity and some of the higher physics classes, because there are some very mind-bending truths in those classes, just unexpected truths about the way the world works that are highly non-intuitive, but still true.
Can you give us an example of one?
So your example about time is relative depending on how fast you're going, which is a very peculiar idea. But it actually, you do the math, and you can even do thought experiments, and we've even demonstrated this experimentally. They took a jet with a quantum clock and flew it around the Earth. It was, much slower than certain multiples of the speed of light, but it still was fast enough that once they had flown it around the Earth enough times, they brought it back and compared it with the original quantum clock, and sure enough, the one on the plane had actually moved a little slower.
Yeah.
Because of the fact that it was going quickly around the Earth.
Right. I remember too, a few years ago, we were in a discussion, and when I guess you were doing your master's work with nanotechnology, and the idea, the applications there, but like big steel girders, we know what those are. But if you want to make things very small, things start to get really weird and unpredictable, or at least certainly more unpredictable. What was your nanotechnology research like? What did you discover in that field?
So I'd say there, I mean, I'll do a little bit of kind of what I worked on, but then also a fair amount of the program I was in, we talked a lot about semiconductors and like computer chips and how computer chips work. And there's some very interesting findings right along with what you're describing there. I mainly worked on graphene, which is basically a single atomic layer of carbon atoms. So it's like, you could almost think about it as a 1 atom thick chicken wire made out of carbon atoms.
Mm-hmm.
And it's remarkably strong, an excellent conductor for its weight. So worked on making that and using it for different types of sensors. We were trying to do, we were making different sensors for light mainly. But we also worked and kind of onto the strange things that happen at those small scales. And also to give a perspective, graphene, just for a sense of how small it is, you can fit on the order of about 100,000 sheets of graphene in the width of a piece of paper.
Yeah.
So it's pretty tiny.
Yes.
I mean, very different scale than what we're used to.
Right. And how do you even, there must be very precise sorts of math, I'm a guess, to be able to work with something like that.
It's definitely precise sorts of methods. They actually, I can definitely go into the technical details, but we don't want to get too bogged down there. But
sure.
It's some very precise methods for roughly single atom layers of this graphene.
And that seems so. And of course, atoms, how do you measure? What do you do with that? Like, you're right. The more we drill down, things get, in a sense, more weird, and in a sense, need to be more precise at the same time. That must be a very difficult challenge.
It's absolutely a difficult challenge. And I think so there's something called Moore's Law in the computer chip world. Part of the reason that computer chips have pretty rapidly been getting faster and faster and faster in computation power. What in the old days, maybe you have a 25 gigabyte computer, and now we're looking at 25 kilobyte computer, and now we're looking at gigabytes. I mean, major difference in computation power. And what's happening is the transistor, kind of the fundamental building block of a computer chip, is a bunch of little on-off switches, which are called transistors. And the size of those transistors dictates how quickly you can process things. But as things get smaller and smaller, you maybe have heard of the particle wave duality for electrons. So electrons, when you get small enough, electrons are not actually, we think of them like little BBs running through a line, a wire. But they're actually waves, and they have a wave function. And that's part of what quantum mechanics talks about. And so that electron is really spread out a little bit in space. And that starts to play tricks on you when you get small enough, because that wave, if you have two very tiny wires running right next to each other and electrons running through, the wire on one side, sometimes it will spontaneously jump to the wire on the other side. And it's called tunneling. And that's a side effect of the fact that electrons are not really hard spheres. They're actually a wave that has some spread out over space, and it has a probability function of showing up in different places. So sometimes it'll hop into weird locations. And obviously, if you have a computer chip and you're counting on, an electron moving through this channel, and then all of a sudden it shows up on another channel over here, it's going to cause problems.
Absolutely. Yeah. So like the computers we're using right now, there's so much we don't really understand at all about, at least certainly I wouldn't, about all the things happening at the microscopic level. But now you're with the Applied Physics Lab through Johns Hopkins, and tell us a bit about, briefly about what you're working on now.
Sure. So I'm working on the PhD right now, and actually I'm really enjoying the work that we're doing. What we're doing is something called additive manufacturing for metals. Another way of thinking about it is it's kind of like 3D printing for metals. So we're figuring out how do you 3D print a metal part, and the process that we use is called laser powder bed fusion, where you spread a thin layer of metal powder, maybe like thin as a piece of paper, and use a laser like a stencil to melt in place the stuff you want to keep. The metal melts and resolidifies at speeds of about 1 million degrees per second. So it's a very, very rapid heating and cooling of this material. And you can take two parts, one built by additive manufacturing and one built by casting or a more conventional technique. And they look the same on the outside, but inside, they're actually significantly different. So the microstructure is different. And a large part of my thesis is figuring out, okay, we can build, let's say, example, you have an airplane and you want to put a part on your airplane wing. We've studied cast metals for decades, so we know exactly how it's going to respond. We're pretty good about its failure characteristics, when it's going to break, all that sort of stuff. But additive manufacturing, even though you can look at the outside and say, it looks the same, when you cut it up and look on the inside, the way those atoms are arranged in the microstructure inside that material actually is different, and that results in different properties. So if I put that on the airplane wing, is it going to break earlier? Is it going to go break later? Is it going to perform better and like last longer? Or is it going to be more susceptible to fracturing? So that's really what we're looking at, is the difference between kind of this new technique for building versus a more conventional technique.
Yeah, and you mentioned to me too that there may be an application for this in space, right? Where you can't manufacture, well, like can't just have like a chest of spare parts, right?
Yeah.
Yeah, and so maybe you could manufacture spare parts or improvements in flight. Is that correct?
That's absolutely correct. And that's a great, yes, you're absolutely right. And that's a great example of one of the unique utilities. Not only can additive manufacturing be used to build really peculiar geometries that you couldn't build otherwise, but if you think about it, keeping an inventory of all possible spare parts on a spacecraft is just not feasible. Like you don't know exactly what's going to break, but having the flexibility of a machine that can build whichever metal part you want, all you need to do is, even from home, send a file of a drawing, like send a CAD file to that machine. So you could, from Earth, if you have someone up there and say, hey, this broke, I need you to send me the file, you can send that file, or even have kind of a directory of all those files on the spacecraft, and be able to build what you need right there. And there might be some limitations. I mean, you can't be rebuilding the entire external shell of the aircraft, but you can build smaller replacement parts and have the flexibility to do that on demand.
Yeah, and I can imagine that this might make longer-term space flight or flights deeper into space a little bit more feasible.
Yep. Yeah, absolutely.
Okay. Yeah, interesting. Maybe we'll have a chance to talk about that too. But what I wanted to shift now, John, is so I meet people who are interested in classical education, and a lot of people, when they initially are interested in it, initially notice, oh wow, the great literature you're reading. Oh wow, it's great, rhetoric, all these great skills that in speaking and so on, and writing and this and that. But even today, I think some people at least, believe that, well, a classical education is great, but it's not really for those who are interested in science. And you have science people, and they should get this kind of education, right? And you have humanities people, they should have this kind of education. And a classical education is a better fit for a humanities kind of person. So here you are, the long list of letters after your name, all involving science. And you're not our only graduate like this. So how would you respond to that? What do you see as the link between the humanities and the sciences?
Sure. So I'd say, I think some of the things that I appreciated most from AFA, and that I think were most helpful in that process, reading good literature and writing a lot helps to build skills of clear and organized thinking and clear communication. Generally speaking, things like critical thinking and also rhetoric. So the ability to convince someone else of an idea. And all of those are highly transferable skills and highly relevant for the sciences. And even one thing, I didn't fully appreciate this until I started getting into the PhD. Things like writing can make a major difference. A well-written article needs to combine with that clear thinking and good experiments. But good writing actually is very important in the higher sciences. Like particularly as you get higher. It's maybe not as obvious when you're doing your, physics problem set, but it's more obvious when you're trying to publish a paper. And you actually need to figure out how to clearly communicate a central story. And actually, that's one thing I've started. Another piece of the kind of repeated practice of AFA that I think is helpful, and something I've noticed is a kind of particular challenge of the PhD side of things, is frequent writing in AFA forced me to begin with the end in mind. So I'd start out on any essay, and I know I'm writing something, but I know I have to tie it together at some point. And so there's constantly in the back of your mind the consideration, well, how is this feeding into my main points, and how am I going to be able to make a cohesive ending to this train of thought. And one of the hardest things, and I was talking with one of my postdoc in my group up at Hopkins, and he was saying that, and I agree with him, one of the hardest things about science is actually figuring out the story for how you want to tie the data together. So it's one thing to do a bunch of experiments, and oftentimes it's relatively easier, kind of like the base level is to do a data dump, where you just say, look, this is all the data I collected, and just kind of dump a bunch of graphs and figures and talk through what, all of these things you found. But the real challenge is winnowing down that pile of data to a cohesive narrative that actually is compelling and that people might find interesting. And that's it's kind of an unusual skill. Most people don't think of that when you think of science, but that's one thing that has, at least I've found it to be much easier to do the data dump, but much more important. And I think AFA helped with some of that training, or that classical mindset, and thinking through the world from that perspective. It's helpful in training to better be equipped to tell those types of stories.
Yeah, John, I think it's fascinating that you use the word story there, and I'm so glad you did, because I felt this way too. I mean, sometimes, well, I think before, like, I was conscious of it, I felt it, but wasn't aware. Like, sometimes I would listen to scientific arguments or try and follow like a scientific argument. I guess I'll put it in quotes, but you get kind of overwhelmed with the chaos of numbers and data, and you lose your way, right? It takes someone, like you say, with a narrative sensibility to be able to take that data and shape it and give it meaning. And yeah, the idea of a story arc too, I think is also fascinating. Can you talk a little bit about that? Maybe something in your own career or something was influential to you, like how a problem set or an experiment isn't in fact a kind of story that you tell.
So I think I will say, I think I've felt the difference between kind of prior, and actually one of my physics professors at Grove City made the comment that maybe 10% of what he learned in undergrad really stuck, and then a lot of stuff really got cemented when he'd seen it a second time in grad school, and kind of later on getting a second round of exposure to some of those ideas and concepts. And I can see some truth to that. I think that some of learning is waves of exposure. So seeing something once is interesting, but it may not necessarily stick as tightly. Seeing something a second time, you begin to start to have it stick a little bit more and tie a bunch of interconnections, get light bulb moments from connecting disparate ideas and concepts together in your mind. And I think that grad school really aids with that. In terms of an example of a story, I think a story can flow out of some of those connections. Mm-hmm. So as you begin to understand more deeply, not just a 117-point bullet list of detailed facts about physics or material science, but really a central theme that flows out into 73 of those bullet points, or kind of influences 73 of those bullet points. Yeah. And I think as you grasp those central themes a little bit better, then you're better able, you have some kind of more foundational connection points that you can use for anchoring your story.
Sure. Yeah, the kind of to at least begin to probe a little bit of the why and not just the how. I heard someone interested. I thought this was really interesting, and we don't often think this way. At least I don't. But he asked the question, "Why is the sky blue?" And the person responded with a kind of, you have light and the refraction of light, and started to give the equation. He just stopped and said, "Wait. That's the how. What about the why? What about the why?" In other words, it could have been different. Like, if you believe that God, made the world, the sky could have been maybe a different color, or could it have been? Like, is there something inherent in the nature of the sky that it must be blue? Or could it have been green, but it is blue for this reason? In other words, to think about, I think the way I've seen science, they're great about the how.
Yep.
And maybe they are limited in the why, and maybe naturally due to the field of study. But I think it's really good for science. Like you say, science starts to make sense when it's connected to the why, connected to an overall, even if it can't fully explain the why.
Yep.
Yeah, what are your thoughts on that? You're the science guy here, not me.
I think you're absolutely right, and I think that connecting to that why is certainly important, and it provides. I mean, honestly, even scientists, part of the challenge of that communication, and something that I've started to realize too, if I'm listening to another scientist and they're going the data dump route instead of a clear story route, I check out too. I mean, like I glaze over. I'm like, I'm losing. You lost me somewhere. And so, even scientists like to have something that's a story. Like to have something where you can understand where you're coming from. There's a good flow. That's one thing we've been working on, kind of in the paper that we're working on right now. Yeah, a good flow of those ideas that bring someone along for the ride. So it's not just, and then this happened, and then this happened, and then this happened. It's a very clear intro, body, conclusion, and then tight threads throughout of that overarching story.
Right there, like, it's not a competition per se, but I mean, it's the papers that connect, right? Whose ideas make sense to people. Who someone can say, yep, okay, let's go with that idea, because, at least I know what that idea is. At least I know what you're talking about. And I know what you want to accomplish, and I see its purpose. So I imagine like the winning proposal isn't necessarily just only the best data, but maybe the best story.
I think there's certainly something to that. And that's something that I not fully appreciated. And actually, I don't remember where I heard this, who I was talking with about it, but even in the sciences, there is some, it may sound bad, but there's some like salesmanship required. I mean, you can't if you're proposing ideas, you're competing with a bunch of other very smart people, and you need to be good at understanding, recognizing, and honoring. It's using some of those rhetorical skills to recognize, okay, what does this funding organization really care about, and how can I couch my proposal and this discussion of things in a way that they would be interested in. And if you go in with the data dump approach, then, I mean, unless you got some really phenomenal, groundbreaking stuff, it's going to be, you need to be good at selling that idea, kind of selling that story. And so that, I think, absolutely, that's an important consideration. It's definitely, there's some side skills that many people don't think of as conventionally scientific that actually can make a big difference. Another piece here. So on the topic of writing and writing clearly in stories, there is a combination. There was an interesting book I was reading not too long ago called Microbe Hunters, which is an interesting story, actually a really fascinating read of a bunch of the scientists who were most influential in discovering microbes, all the way back from like 1600s time frame, kind of the different generation of all these different thinkers. And one of the common threads of many of these scientists is some of the greatest discoveries begin with an intuition and are followed up by thorough experiments. So there is a creativity component at the start where they have a sense of, they see something weird, and then in their mind, before they've maybe tried and generated experiments to prove something out, in their mind they think, I think I know what the answer is. I think this is what's going on. And then they carefully design a very definitive or clear or clever experiment to tease out whether or not that intuition was correct. And that's oftentimes people think of science as the cold analytical side, but I think that it's not entirely divorced from the creative side. Some of those greatest breakthroughs were rooted in some level of imagination, like reaching through that data and thinking, I think I know what's going on. And then afterwards, constructing the very clear experiment to demonstrate that. And some of the best papers, so there's a combination not only of writing clearly, but also that thinking clearly is very important as well, because a good experiment does require forethought. And sometimes you read papers and you can see that someone they were really clever. That experiment maybe is elegantly simple is one way to think about it. And there's something to that as well that flows out of a foundation of clear thinking about a problem.
Yeah. Very good. Very good. Well, John, those are great thoughts. Thank you. And there's a lot to chew on there. For our final segment, just for a few minutes, you're working with space. Well, you're working with something kind of related to the space program,
Yep.
and I'd be curious for your thoughts on the exploration of space in general. So, kind of like two sides, real quick. There's the side that says we have to keep exploring, we have to keep expanding. Like, this is just part of what it means to be human, to be made in God's image, to explore His creation, to get to know it. Some would say there's a theological dimension. Others might say there's just even a kind of practical dimension. There has to be something, shall we say, outside of Republican, Democrat, red state, blue state, or whatever, to unite us, to inspire us. Space is that place to do that. And others would say, look, it's very expensive. We've gone as far as essentially we can go. Clearly, mankind, we're not meant to be out there. The littlest thing goes wrong and everything, people die and all of the money spent, we could use it so much better to effect real good and real practical change here on Earth. Where do you stand on some of these questions? Like, what would you say about the efficacy and the utility of the space program?
Sure. So I think there are definitely a couple layers to that question. I think that, for one, I think there are some branches of the space program that are based on understanding the environment immediately surrounding Earth. So there are satellites. There's actually a project that I was working on that's looking at ions in space and trying to understand the ionosphere around our Earth, or potentially, I think it's mainly around our Earth is kind of the goal there. And I think there is some overlap. Technology that's developed for understanding our immediate environment and understanding, and even understanding things like the ionosphere or understanding how satellites work. They have improved our lives. I mean, GPS, for example, is a very simple example of a way where space research has significantly changed the way we communicate and the way we can locate ourselves on the globe. So there's certainly, I think, merit there just from a quality of life on the human, on the Earth.
Sure.
And I think there is some overlap. Technology developed in the interest of figuring out that around the Earth environment may help get us partway there to some of the longer term. So kind of investing in that near term may actually build a little bit of foundation that we can then use. So rather than starting from scratch to move into the next domain, we actually have some knowledge that we know. And so it's a much smaller jump to make the next technological leap. And I guess it does get into, unfortunately, I don't remember maybe it was Pascal. I don't remember who it was, but maybe it was Pascal and Bacon, maybe, are the two, where in terms of the philosophy of science, is the goal to find truth or to alleviate human suffering? And I think those are two different perspectives on what's the main purpose of science. And I think there's value in both of those things. I mean, I think there is, like quantum mechanics, there's some very unusual quantum mechanics and relativity. There are some unusual findings that we get that come from looking at the stars, relativity in particular. There's a lot of things that you gain because you're dealing with much longer distances and larger time scales and those sorts of things. You get a little different window into relativity, like redshift and blue shift, and understanding certain aspects of that.
Right.
So I guess I think it comes down pretty heavily onto where you fall in terms of is the primary goal of science to alleviate human suffering, or is the primary goal finding truth, or is it some blend of the two, or should it be, it seems like there's a balance between it's exclusively one, exclusively the other, or it's some blend, and then you can discuss the balance of the blend.
So you would say the space program, it does both. It fits both of those tasks of science. It has, in fact, more practical benefits than we might suppose.
I think, yes, definitely in some areas. And I think there are some areas like APL, for example, has done some really neat missions on understanding the sun a little better. I think Solar Probe Plus is one that they're working on, and they did one recently called New Horizons that recently passed Pluto. I think it was a summer or two ago, that flew out a while ago and then passed Pluto and gave us more information than we've ever had before on Pluto and kind of what learning about the asteroids out there.
So this this job you're working on now in these 3D printers, do you think that they are, how close do you think you are to getting it so where a spacecraft could manufacture a spare part somewhere between here and Mars?
You know, I think we're moving in that direction. I mean, that's a great question. I think it depends a little bit on the core requirement of the part. So additive manufacturing, and just kind of a clarification on, well, yeah, additive manufacturing, particularly of metals, these are very sophisticated machines, and it's not like, you know, many times people think of 3D printers and they think of the little plastic one that you have on your countertop in the kitchen, you know, and you can make some little trinkets out of plastic.
Right.
The metal machines, I think they cost about $1 million a pop. And so, and they have a team of people supporting not only making the part, but also sometimes a supporting machine shop to help cut the part loose and kind of do some final finishing. So I think that the spacecraft situation, we might be able to do some types of parts if you're not worried about things like surface finish too much. You might be able to build some types of parts, you know, as we stand now. If you want to get a little bit fancier and maybe do some more intricate things, if you, depending on the application, we might need some more development. But I think we've got, I mean, the technology, there's a lot to learn, no doubt about it. But depending on what you need it for, it's also, I mean, it's capable of doing some things, even as it stands now. So
that's great. That's very exciting. John, it's been great to hear from you today. I really thank you for the time you've donated to us and for the wisdom you've shared and the story and your story about science. And maybe one day soon, that laser gun, if you ever get a laser gun, send me one too. To, like, I want to relive my childhood fantasy.
Sure.
Very good. Ladies and gentlemen, John Fite. Thank you very much again, John. I hope you have a great day, and good luck to you with your applied physics and your studies at Johns Hopkins.
Well, thank you very much, Mr. Mathman. It's been a pleasure. Thanks a lot.
All right, great. Thank you again, ladies and gentlemen, for joining us, and we'll look forward to another episode soon. Have a great one, everyone. Bye-bye.
Bye.